I'm just gonna, I have a baseline story, and then we're just going to talk about stuff, or all of the systems, and I'm gonna try my best to color code things and remember what colors are what. Actually, I'll write it down. I brought more papers than I need, so. Okay. So I'm gonna do kind of like a flowchart thing. I don't know how you guys are doing it. You guys might be doing drawing or whatever. I'm just gonna do flowchart. Let me get this to focus.
I prefer not to draw.
All right. So first bullet, it's a hot day and a hot sunny day or hot day, and Bob is standing outside eating a hamburger. So we can start off with the hot day and its influence on his excretions from his skin, or we could start off with the hamburger and we could take that in that direction. What do you guys want to start off with? Hamburger time? Let's do hamburger. Okay. All right, so Bob takes a bite of the hamburger. So what's the first thing that happens? It's going to go into his mouth, and what's going to happen?
Mechanical digestion begins.
Yeah, mechanical digestion. Amylase too, so he's going to secrete amylase. So we can take it both ways, because both of those are different systems. Chewing is like muscle and nerve, and well, amylase is nerve and excretions. What body system is that? What is it?
Which one?
The secretions of fluids from ducts.
Oh, endocrine.
Huh? Not endocrine.
It's metabolism. Yeah, digestion.
What's sweat? What about sweat? What system is that? Integumentary. Would secretions? I might be digestive. Would secretions from the mouth be integumentary, or would it be digestive?
Would it?
But I mean, you're also secreting like lysozyme, and
I guess it depends on how you go with your story.
I guess you can pick either one.
The lysozyme, if you want to talk about like salivary amylase, basically one of those big guys in the mouth.
Okay. Well, let's just start off with salivation, okay? Before we go into like the muscle and bone, actually be bone, right? Because the muscle's attached to bone. Okay. Anyways. All right. So let's see. Did she at any point go over the nervous signal that would trigger salivation? Okay. We'll just start off with, so salivary glands secrete saliva containing amylase. I don't need to put the comma there. We'll just put amylase and lysozyme. Oh, and mucus, right? Amylase, lysozyme, and mucus. And so your amylase is going to break down starch, and then lysozyme is going to break down bacterial cell wall. And you can color code those in any way. I guess I'll go with digestive system with green. Okay, so now we can talk about chewing, right? So chewing, that's going to be nervous and muscle. So I'll make this lighter blue nervous signal. So cranial nerve, five, trigeminal, branching to the motor component of mandibular division signals. Because that's going to control all of the muscles involved in chewing, right? And so let's just talk about the ones that she mentioned in 241. So I know that Aaron, you've got a set of 4, right?
Say that again, sorry.
The chewing muscles.
Yeah, the 4 muscles of mastication, she really focused on 241. Masseter, temporalis, lateral medialis.
Okay.
The lateral being the only one that was
Okay. So we're gonna roll with those. Okay, so let's list them off. So muscles of mastication, that was one, right? And then you said temporalis. And then the medial and lateral pterygoid muscles, or yeah, we'll just say muscles of mastication, temporalis, medial, lateral, pterygoid, chew food. Okay, so I'm gonna make a side note so I can keep track of all of the colors. So we got green, digestive, this cyan color is going, oh, thank you, nervous, and then orange is going to be muscle. Okay. Okay, so we can go back to taste. So we're using nervous signal to control the muscles of all of the muscles that are going to be involved in chewing the food, but we're also tasting the food. So we might as well talk about that to just hit nervous signal even more. So all the while, taste receptors are sending signal through the glossopharyngeal nerve, nerve 9, and then if we even another parentheses, which is going to that's going to account, we'll just say accounting for the posterior 1/3 of your tongue. So all the while, taste receptors are sending signal through the glossopharyngeal nerve, accounting for the posterior 1/3 of tongue. You can just put it tongue. facial nerve. So that's going to be 5, 6, 7, right? 7. Facial nerve, counting for anterior 2/3 of your tongue, and your vagus cranial nerve 10. Which is going to be accounting for the back part of your oral cavity. So how would you say that? The vagus nerve and its taste. That's going to be like the ending part, the very back part of your oral cavity. Well, we got the last 1/3 of the tongue is going to be the glossopharyngeal. Then the facial nerve is going to be the anterior 2/3. But then like your vagus does account for some of like the really bitter stuff in the very back. Huh?
The Vegas does too much stuff.
Yeah, it does a lot of stuff. Accounting for rear oral cavity. You can word it however you want. So all of this. So we got sending signal through glossopharyngeal nerve, facial nerve, and vagus nerve to the gustatory cortex. That's where you're processing that taste. And your gustatory cortex, just to break that down, just so she can't say that you didn't talk about it, it's going to be anterior insula and frontal operculum. I don't know if the operculum has 2 P's. Fact check really quick. I'm going to use Google, don't yell.
Mm-hmm.
Operculum. I suspect it's 2 P's.
Yeah.
Nope, it's only
They're
1
on my
P.
basketball
Okay.
because it's too light.
Okay. So that's chewing. We got saliva. We've got nerves signaling to our muscles to chew, and then we've got taste. No, I think it's the smartest thing to do in this story, where we're talking about stuff, is to we want to eventually get to releasing hormone. And then a hormone that's super easy to talk about is insulin, and so we should maybe focus on the sugars. So maybe you instead of eating a hamburger, to just really drive home that point, you could say he's like licking ice cream on a hot day. I mean, that would make more sense too.
Mm-hmm.
Standing outside eating ice cream on a hot day, full of sugar, probably going to spike your insulin, and we want to talk about that mechanism. At least that's what I would do, just because it's just easy. You want to go with easy stuff. Okay. So we got taste. So what happens? What happens? What color did I do for digestive? Okay, green was digestive. Okay, so we chewed the food, we tasted it. Now we're gonna send it down through our pharynx to our esophagus, and then through that lower esophageal sphincter into the stomach.
What if he choked on it? Like his
Ooh,
epiglottis?
So yeah, you could say you could even mention the epiglottis. So while swallowing, the epiglottis full, and she really emphasized folded backwards and downwards, right?
Mm-hmm.
And then you could even color code that to like hint or foreshadow the respiratory system. Do you want him to like full on choke or?
No, not full on.
Oh, okay, okay.
But like, I mean, just like, you know.
Because
his
we could talk about
epiglottis
like
and
the
then,
depth.
and then like
'Cause
suddenly
there's lots of
he has to
biases.
like start coughing.
Okay.
And then
Okay,
yeah.
so it's like it gets in and it tickles his carina and then
Tickles his carina.
and then he coughs it out.
Okay.
Or well, I think what we should do is we should just keep it keep it just mention the respiratory system. I don't know what color I should use for that. Blue.
You could
Blue.
talk about the
Like a dark blue.
hormones. You could talk about the hormones and the duodenum.
Oh yeah, we're gonna get there. Yeah, once we hit the digestive system, it's like all free game. So, we got digestive, which is green. Okay, so let's just talk about it hitting his pharynx first. So, food moves to his pharynx, and then what can we say? Let's just say that the his epiglottis. How do we say this? Food moves to his pharynx. We can just make another bullet here. Bob's epiglottis folds. Would we say folds? Moves backwards and downwards to close the opening. Backwards, downwards, or downward. I think that's the proper English. Backward, downward, instead of the S. To cover what? What are we covering?
His trachea.
Yeah, to cover the trachea. Or what do we call the opening specifically? Huh? Okay, well, to cover the trachea. I thought there was a name for it.
There probably is, but I don't think we had to learn it.
Larynx?
Well, larynx is like the voice box. Like, I mean, it's the top.
Yeah.
But she said, there was actually one question where on the lab test where it was she either accepted trachea or larynx.
So she can.
So
Okay.
I think it's
okay.
kind of interchangeable for her.
I guess cover trachea. I guess we could say to prevent food from moving through his trachea.
Mhm.
So I'm gonna cross this out. To prevent bolus from entering his trachea. Look at that foreshadow. Like, hey, because once the nutrients get into the bloodstream, we're going to talk about heart, and then we'll probably talk about respiratory. Okay, so Bob's epiglottis moves backward and downward to cover or to prevent bolus from entering his trachea. So moves from the pharynx, and then we could even, I don't know how you guys would do this, to the esophagus. What you probably could do is indent this one as kind of like this whole part right here, like indent it, because it's kind of like a sub bullet. Okay. So food moves from his pharynx, moves to his pharynx, to the esophagus, to his esophagus, and then from your esophagus, past, through. And what was the sphincter? What did we call it besides the lower esophageal sphincter, which actually makes sense? It was like the respiratory sphincter or the cardiac sphincter. I mean, it makes sense. The naming makes sense because of its location, but I just feel like lower esophageal sphincter just more intuitive. Through cardiac sphincter into stomach. Okay, so once it hits your stomach, you actually what that does is it slightly increases the pH, because remember our stomach has very low pH, and that bolus is actually going to influence the pH of the fluids in your stomach. So it's actually going to spike it a little bit, and that's going to trigger your G cells to release gastrin. So what color should we use for your endocrine? Because we'll just foreshadow endocrine. Actually, I don't know if I have any more colors. Am I already out? Red? I want to say red for blood.
you have like yellow or something?
Got a highlighter. Does anyone have like additional color that we'd be able to see? Actually, hold on. You might be able to see this color. Let me just test it out real quick. That'll work, right? The
What?
green? This green right here?
No, can we turn off some of the lights though?
Yeah,
'Cause
sure.
it's a little too.
Okay. Yeah. Well, I got this green. Okay. We could probably move to another paper at this point. Let's just move to another paper.
What's going on?
Oh yeah, brown one. Oh, that's a good color. Thank you. Whoa.
Is that too dark? Yeah.
Uh.
I think you. Whoa.
Did that help?
A little bit.
Yeah, I guess getting rid of that light there might help. Yeah, that'll probably help. Okay. Cool. Okay, brown. I'll use brown for something else. Okay. Alright, so it's a hot day, blah blah blah. Bob chews stuff, swallows it, moves into his stomach, and we want to talk about how that pH change is going to do stuff. So from the top, I would say the increase in pH. You see that? Oh, is that too light? I'll use brown. Is that better? Increase in pH causes G cells to secrete gastrin. See, now we're gonna get some secretions going on, and we would just call this digestive, right? Like if you're getting like hydrogen ions and chloride ions secreted by your parietal cells, we would call that digestive. So, what color is digestive? Green. Okay, dark green. All right. So then I would say parietal cells secrete hydrogen ions and the chloride ions, and we'll say, and you'd probably get mad if you said secretes hydrochloric acid. You want to say secretes these separately, which join in the lumen of the stomach. And so that, which activates pepsinogen, and if you want to get spicy, you could say a zymogen. Activates pepsinogen into pepsin. And then in parentheses, your pepsin or your pepsinogen is secreted by sheep cells. And you can even say which digests, chemically digests protein. We would say food or chyme is churned in your stomach. Chyme exits through pyloric sphincter duodenum or duodenum with denum. And then we could say this lower pH. And I would probably go with, yeah, I'm gonna go with hormones here. This decreased pH, what's that gonna do? What's that gonna trigger your, the cells within your duodenum to secrete? What hormones?
CCK and secretin.
Secretin and CCK, right? Yeah. And what kind of cells are they? They're your enteroendocrine cells. So lower pH causes enteroendocrine cells of duodenum to secrete. You could spell out cholecystokinin, or you can write CCK, and I don't know if you want. I don't know what you want. And secretin. So we can indent here, and we could say CCK causes gallbladder to release bile. And what's the bile do? Emulsifies fats. And then your secretin causes your pancreas to release pancreatic juice. And then you can even put contents containing. What's it contain? Bicarbonate, yeah. You got that lower pH, you're signaling for something to neutralize it, because all of these enzymes that you're going to secrete through pancreatic juice, they work best at neutral or slightly basic pH. So containing enzymes, and you could even probably put zymogens. If you guys wanted to go down that path of the zymogen activation, that's up to you, but just know that there's zymogen activation in the duodenum or duodenum. So containing enzymes and bicarbonate. At pretty much any of these steps, you could branch off and go on tangents about like anything. Like every system is involved in everything. Okay. Okay. Sugars. Remember, we're going along the path of we want to hit up that pancreas and talk about those hormones. So we'll focus on sugars. So sugars are broken down into monomers by Rush order enzymes, and they could be brought into your cells. They could also be brought into your bloodstream. we'll say a cell's bloodstream. Ooh. That'd be a good opportunity to introduce blood, and we want to talk about blood now. Or we could say blood to the hepatic portal vein to your liver to your inferior vena cava. And then we can go through the chambers. So inferior vena cava to your right atria, right? And I'm just going to use acronyms here. To your right atria, through your tricuspid, to your right ventricle, through your actually hepatic portal vein. Maybe at this point we could say brought into cells into deoxygenated blood. I mean, because this blood is going to be like low in oxygen, and now it's high in nutrients. So you could say low O2, high in nutrient. So low O2, high nutrient through the hepatic portal vein to your liver, to your inferior vena cava, to your right atrium, tricuspid, right ventricle. Now we're edging towards your pulmonary system. What valve is it going to exit? Your pulmonary valve, right? What color should I use for lungs or your respiratory system? You want to try that color?
Green?
Yeah, it's like a light green. Okay, right.
Is it a green one?
That's the only. Well, yeah, it's the only light green one.
This is a little number, and not as dark as the other one.
All right. So okay. So anyways, we got right ventricle to your pulmonary semilunar. To your capillaries of the lung. Huh? That's actually light or darker. It's a little darker. It's got more green to it, more blue, I guess. Let's start a new paper. Okay. Oh, that's the key, huh? I don't even know where we're at. Okay. O2 from air will diffuse through simple squamous epithelium of alveolus through simple squamous epithelium of capillary through membrane blood cell into deoxyhemoglobin to make it oxyhemoglobin, right? All the while, CO2 diffuses or disbinds from your hemoglobin into alveolar space. Ah. Is this internal or external respiration?
External.
External respiration. External respiration. Blood moves to your heart. And so here I'm gonna, just to save time, you can talk about all the chambers and stuff of the heart. Aorta. And it's gonna go two different ways. Well, it's gonna go many ways from here. So you can go to the pancreas, you can go to the kidneys. So it depends on what you want to talk about. Let's talk about the pancreas. So that was like the main thing, right? So do we have anything for any colors for endocrine? Do we talk about endocrine? Oh, I had blue. Blue was dedicated to the lungs. Okay. Oh, and okay, whatever. Might as well just use blue then for. Blue was your respiratory. All right, so blood goes to heart, to aorta, to your pancreas. We're also probably going to want to talk about kidneys. What color do we want our renal? We can make it black. Kidney. Well, we want to talk about the pancreas first. Okay, so pancreas releases insulin, or actually within your pancreas you have your beta cells. Releases insulin. Or actually, even if you want to get more specific, don't you have chemoreceptors within your pancreas that detect the high sugar levels, which then will cause the release of insulin. I'm just gonna say, I'm gonna make a side note, I'm not gonna put it into the sentence, so chemo. So if you use this part, make sure you mention chemoreceptors, which leads to your pancreas beta cells to release insulin into blood. I don't know how much farther we want to go with that, because we could go on that tangent on how that's going to interact with all of your cells to cause them to express the glucose transporter. And we could do that. We'll just, and that'll be it. So pancreas releases insulin to the blood, causing cells to take up free glucose by expression. She talked about the expression of the glucose transporters, right? And that'll be it for that. I don't, because that can go really far too. Okay, kidney. Let's see, where are we?
What artery goes to the pancreas?
Huh?
What artery goes to the pancreas? Do you know the name of it?
The artery that goes to the pancreas?
Yeah.
Ooh, does anyone know? I don't know off the top of my head. Let's see.
Yeah.
That's actually a really good question because she's looking for specific things like this. It just says aorta.
Okay.
Splenic artery, arteria, caudae, gastroduodenal, superior mesenteric artery. There's a lot of arteries that
That's
go.
okay. Well, we can just put the renal for the kidney, the renal artery for the kidney. Then that'll be fine. I just wasn't sure.
Oh wait, you said kidney?
No. I was just saying what's the pancreas, but we can just do the renal for the kidney.
Oh, okay. Okay, so yeah, well, there's a bunch of branches off of the aorta that will implant itself into the pancreas. And if you guys want to get into that, that'd probably be good information. You could say from the aorta you have this branch, and this branch, all going to the pancreas. And then for your kidney, you've got your renal artery. Is that what you said? Renal artery. Or aorta to renal artery. Okay, we don't have that much time, so let's try to pound this out. So now we're in a nephron. So kidney. Into a nephron. I mean, many nephrons, right? But we just want to focus on one thing. We want to hone in on one item. So we have our afferent arterial, which leads to your glomerulus, dropping off filtrate into Bowman's capsule. While the big six are maintained inside of the bloodstream, so, and I'm going to put big six with an asterisk, so we don't have to write all of it out. Big six, oops. Big six stay in blood, should in a healthy individual. This person who's eating a hamburger is healthy. Okay, so big six stay in blood. Okay, so Bowman's capsule, which leads to your proximal convoluted tubule, right? What percentage of the filtrate is reabsorbed here? We can just say the majority. Now, how is this stuff absorbed? You've got transcellular, transport, or transcellular, paracellular, diffusion, transport. So this is in between cells, this is through cells. Transcellular would be through cells. Passive active, transport, diffusion, and osmosis. All this stuff is going to be solute. We could even say sodium's going to play a heavy role. So sodium transporters. Reabsorption. Remember your sodium uses symports to bring stuff in. So usually there's like a concentration gradient that makes sodium want to enter cells or leave cells, and well actually in this case it wants to enter your cells, and what you do is you allow it to enter cells, but as a cost you bring it in with a nutrient that you already have a high concentration of, like glucose. We'll just say promote reabsorption of glucose, bicarb, amino acids, water, chloride, lactic acid, vitamins, nutrients. And this is probably where we're out of time. But so you're at the proximal convoluted tubule. We know that after that you go through the loop of Henle. You got to mention your aquaporins. You want to mention the transporters that bring sodium out, and then you're at your distal convoluted tubule. And then from your distal convoluted tubule, you want to make mention of the collecting duct, then the minor calyx, then the major calyx, then the pelvis, then the ureters. No. Yes. Then your ureters, then your bladder, then your urethra. And then it's also hot, so this guy's sweating. You want to make mention of the mechanism that's going to trigger him to sweat, which would be your preoptic area of your hypothalamus. Hypothalamus? Yeah, your hypothalamus, which has thermoreceptors that tells your body to sweat, but in a very specific way, not just body to sweat. I wouldn't write tells your body to sweat. Yeah, it's going to cause vasodilation because it's hot, but then you're also going to, you really want to make mention of the sweat glands, because that's another. Yeah. Evaporative cooling, the sweat, and those are going to be through your eccrine glands that are going to secrete the sweat. So hopefully that helped.